All right, we're going to start diving a little bit deeper into these intermolecular forces. So have you ever had any of these burning questions here? Like, why do some solids dissolve in water, but other solids don't? Or why are some substances gases at room temperature, but others are liquid or solid? Or what about what gives metals the ability to conduct electricity? And what makes non-metals brittle? Or why do some substances have high boiling points and high melting points, but other substances have low boiling points or low melting points? Well, the answer is because of intermolecular forces, those forces of attraction that exist between the molecules. So there are three types of intermolecular forces that are going to be found between covalent molecules. These three intermolecular forces are London dispersion forces, which we abbreviate as LDFs, dipole-dipole interactions, and hydrogen bonds. Now remember, these are intermolecular forces. So they are not found in the molecule itself, but they are found in between two molecules. So we're going to first start diving into London dispersion forces. Now, London dispersion forces are caused by temporary dipoles. So we saw dipoles in the polar bonds, and these are partial positive and partial negative charges. So when we have temporary dipoles, those are just created because of a momentary moment, that was stupid, but just an instant where you have a partial negative or a partial positive on one side of the atom or the other, but then it moves around and now one side is slightly positive and it's slightly negative on the other side. And this is because of the constant movement of electrons around the nucleus. I'm going to stop sharing this really quick, and I'm going to pull up this video that I have, a little simulation, if you will, showing you what I'm talking about with these, the movement of the molecules. So here we go. So you can see here that we have an atom. The nucleus is going to be blue, the electron cloud is gray, and you see how that electron cloud is changing shape? And we're seeing those dipoles, those little funny little S-wiggly things with the positive and the negative, and how those are changing based on how the atoms are interacting with nearby atoms. And so it creates this temporary attraction to nearby atoms when the electron cloud shifts and one side is slightly negative because of the increased amount of electrons on that one side at that particular time, and the other side is slightly positive because there's less electrons at that point in time. The slightly negative end attracts to the slightly positive end for that instant until it moves and is now attracted to another side. So let me pull this back up here. So those are just temporary because the electrons are constantly moving around the atom, okay? So there's different things that can affect the polarizability or the ability to get these electrons moving more towards one side or the other side. So polarizability increases as you go down the group on the periodic table. And that's because as we go down the group, we know that we're increasing energy levels. So we have a larger electron cloud. If we have a larger electron cloud, the attraction with the nucleus is a little bit weaker, and so it makes it easier to distort and change that electron cloud and get those electrons moving. So for an example, we would see that iodine would be more polarizable than fluorine, and the electrons would move a lot easier because the electron cloud was bigger. Now polarizability is going to decrease as we go left to right across the period. So if we go back to periodic trends way back in like October or something, we were talking about as we go left to right across the period, our effective nuclear charge is increasing because we're adding more protons into our nucleus. So when we have a greater positive nuclear charge, we have greater attraction to the nucleus, and that results in less flexible electron cloud. So it's harder to get those electrons moving the way that nearby atoms want them to move. So then we would say that sodium was more polarizable than the argon because they're in the same period, but sodium has less protons in its nucleus, And so those electrons are more easily influenced by nearby atoms. And then the other polarizability trend is the length of the molecules. So longer molecules are more polarizable than compact ones. There's more surface area, more things can get around that particular molecule if it's longer, and the electrons can get moving easier. So you can see here, down here at these two pictures, we've got the same amount of carbons, we've got the same amount of hydrogens, but this one on the left, because it's a longer chain, is more polarizable. We can get the electrons moving easier because we can get to those electrons easier than if things were more compact in this picture on the right. So London dispersion forces, LDFs, are created in between molecules because of those temporary dipoles. Because as these electrons are moving around in the electron cloud and it's creating these little temporary dipoles, it's going to form a momentary attraction with a nearby atom or molecule. And it's going to induce a dipole on that other molecule. And that slightly positive and slightly negative ends of those two nearby molecules are going to slightly attract each other and create a really quick interaction between those two molecules. Before those electrons move, that attraction is broken and attraction is formed to another nearby atom or molecule. Now, because everything has electrons and everything has electrons that are always moving, every type of substance would experience London dispersion forces. However, these are the only forces that you would see in nonpolar molecules, because nonpolar molecules don't have permanent dipoles because the electrons are shared equally. So that's why it's really important to draw those covalent molecules to determine the bond polarity and, more importantly, the molecular polarity, because it says that the only IMF, that this is the only IMF in nonpolar molecules, because we have to figure out, well, is there a lone pair on that central atom? Are all of the ends the same? Or is it symmetrical and it would only experience London dispersion forces with other nearby atoms, right? And it says up here that dispersion forces are usually going to increase with molar mass. So that's something else that we can look at. We can look at the size of the electron cloud. We can look at the effective nuclear charge. We can look at the molar mass to see which dispersion forces are going to be greater. So let's take a practice here. It says, under similar conditions, LDFs are strongest in which of the following samples? So you can see all of these are noble gases. So the one that would have the strongest LDF is going to be the one that has the largest electron cloud, because they're all in the same group. So going down the group, the biggest one would be the krypton, and it would have the strongest LDF. Let's take a look at this question here. It says LDFs between molecules decrease with, so we talked about a couple of things that you would see LDFs changing with. So let's take a look letter by letter. Letter A, increasing number of electrons and increasing the distance between the molecules. Well, if you're putting more distance between the molecules, are you going to be able to influence, let's say you're this atom or molecule here, and you put more distance, are you going to be able to easily influence the electrons in this one if you're putting more distance between them? No. I think we can get rid of any answer choice that says, it says decrease, I'm sorry, decrease. I think we can get rid of any answer choice that says decreasing the distance, because if you're getting closer, you're going to be able to influence those more. So that means we can get rid of B and D, because those both say decreasing the distance with the molecules. So that leaves us with A and C. So the question again says LDFs between molecules decrease with, was it going to decrease with increasing number of electrons? Or are those LDFs going to decrease with decreasing number of electrons? Well, our answer is going to be letter C here, decreasing our number of electrons. If we have more electrons, we have more opportunities to get those electrons moving and to polarize that atom or the molecule and get those temporary dipoles if we have more electrons. All right, so if you have any questions about LDFs, let me know. Thanks.